is recorded by her. Got it. Thank you for attending my talk on a universal particle structure that gives all particles their properties. This is a brief presentation on particle physics. It uses only known particles, forces, and physical constants in three space dimensions and time. It describes the physics involved and then uses what I call the simplest possible maths to accurately determine the magnitude of the physical effect that they generate. Now, it suggests that to be complete, a particle physics theory should also show how their structures and properties combine to give the world we see around us. So, but before I start, just to show one example of how this works, I refer you to this paper, which you can view at either of these addresses. And the physical principle that Einstein used was that he applied Newton's gravity to photons that had mass. And that was a paper he wrote in 1911. In 1916, in his foundations paper, he went through and developed a whole lot of field equations. And people who solved those field equations believed that they predict black holes from them. Einstein didn't believe in them. And when you go through his mathematics carefully, you can find that in order to derive black holes, they needed to make three mass errors and not understand some simple physics. For example, Einstein derived G11 equals minus 1 plus alpha over r, which he then approximated to minus 1 over alpha minus r, and that is the solution, that is the equation used in the so-called exact solution. At the same time, he derived G44 equals 1 over 1 plus alpha over r, because they are the negative inverses of each other. He approximated that to 1 minus alpha over r, and that is what is used in the so-called exact solutions. When you go through it all, and you can reduce, well, get four metrics out of it. Newton's metric, Gm over r squared. The exact solutions to Einstein's field equations become Gm over 1 plus alpha over r times r squared. Black holes, one is called 1 minus alpha over r. The exact solution to the physics he used is I call it Gz for redshift, Gm over r squared e to the alpha over r. That actually directly predicts the structure, the torus-like structure observed from the center of galaxies. But the main thing that comes out of this, or one thing comes out of this, to understand Einstein's gravity, what Newton called r squared becomes, under Einstein's gravity, r times 1 plus z. So what Newton called r becomes r times 1 plus z, where z is the redshift. So this equation, I think, is relatively easy to use. It's not much more difficult to use than this one, which makes understanding Einstein's gravity considerably simpler. Now, if you have a look at both of these equations, they show that Einstein's gravity is weaker than Newton's inverse square law. I mean, weaker gravity means that Mercury orbits a little further away than it otherwise should from the sun. It's also attracted by a weaker gravity, so it takes longer to return to its perihelion position, and therefore it returns to it a little bit later in each orbit, and that is why Mercury's orbit precesses. Now, gravity being weaker than inverse square, causing a planet's orbit to precess, was worked out by Newton in 1687. This weaker than gravity is entirely consistent with that. But I'm just using that as an example to show that if you know the physical principles, you can in fact get the maths much easier and get rid of any errors that, or have the possibility of eliminating errors. But when it comes to particles, I think the best way, I'm going to start out with universe zero, and we've got matter-free space. And we do, it's got electric permittivity and magnetic permeability. And I think we all know that that means if you've got a positive disturbance in one direction, you have an electric field disturbance in one direction, you have a magnetic field disturbance perpendicular to it. And this is highly schematic, of course. Positive making one cycle, magnetic field making one cycle. Of course, we all know conservation principles. Positive field in this direction equals a negative field in this direction. A north magnetic pole in this direction is a south magnetic pole in this direction. So this you could consider it's a pictorial representation of a single wavelength, plane polarized photon under the Einstein-de Broglie model. It's what they call psi, their wave function. And as Maxwell's equation said, this whole structure then moves at the speed of light, c, given by the square root of 1 over the square root of epsilon naught mu naught. Now, photons have mass. Einstein pointed that out in 1905 when he did his special relativity theory. Now, the photon's mass is in its electric and magnetic field. Now, in this particular case, the wave properties of a photon come from the wavy nature or sinusoidal nature of the fields. The particle property comes from its limited wavelength. This brings us to what we call Heisenberg's uncertainty principle. The photon is contained within this dimension. You can't define that accurately to a point, and that's essentially the physical origins of Heisenberg's uncertainty principle. The other thing is that in most photons, these two fields rotate through 360 degrees in one wavelength, and they become what is known as circularly polarized. I've tried here to indicate, using the arrow notation for strength, the situation of the positive field rotating through 3 wavelengths, basically 6 times. An indication here of all 4 fields sort of side on is not very clear. It becomes a little bit clearer here. Then what happens is that if this whole structure twists through 180 degrees, or through 360 degrees per wavelength, then when it twists through 180 degrees, this is now on this side. And what you have is that all 4 fields, north and south magnetic pole and positive and negative electric charge, are all in particular quadrants. The thing about a north pole in this direction and a south pole in this direction, but a south pole pointing down means a north pole pointing up. So the magnetic fields become continuous. Now, for those interested, you can, this is the Einstein-de Broglie wave function for a single wavelength circularly polarized photon. Other representations are possible. And the other thing to realize is because this has mass, the circularly polarized photon, with the whole field turning through 360 degrees every wavelength, it gives a twist or spin, or as we'll show later. It's measured at a value of h-bar. So that's the other thing to bear in mind is space supports photons. So now for those who are maybe skeptical or prefer the standard model of the point particle, this is an image of a single photon that was taken by Romero, and she was part of a team. You'll see here the magnetic field is continuous. And the electric fields, well, I think we're all aware that if a positive field comes close to a negative field, they cancel each other out, and this gives the two black spots in the middle of the photon here. So I respectfully suggest that the model I'm using has a very good representation in physical reality. Now, how do we get from photons to particles? Well, it's been known for a long time that photons can generate particle-antiparticle pairs. At the same time, antiparticle annihilation generates photons. There's been long established a good relationship between photons and particles. Now I'm going to use a model that was first published by Williamson and van der Mark in 1997, and when they were applying it to electrons. And they literally said, and it was the fact that the photon, they proposed the electron was a photon making 2 revolutions per wavelength. And I'm suggesting that that is the universal model or universal structure of all particles. And I'll go through and show how it works. First, this is schematic illustration, quarter wavelength, half turn, half wavelength, full turn, right through to full wavelength, 2 terms. I don't know where that came from. Oops, what did I do? I did wrong, just hang on. Just bear with me for a minute, I pressed the wrong button. Share screen. No, I don't know.
I have a question. You have shown some Romero article. Could you send show some reference? I was able to find it.
Yeah, I don't know what
paper, but Romero. Could you go one slide back?
Yeah, new share. Share. How do I?
We can see it again.
Yes,
oh, okay.
Yeah, I'm trying to get the whole the play screen up. I can't seem to fire that. Where does it play? I'm just going to have to unmute chat. I'm not sure where the play button is supposed to be. Can I turn this to play? Oh, there it is, play. My apologies for that. I'm not quite sure what went wrong, but just to resume. That gives the photon, the rotating photon, a radius of its wavelength divided by 4 pi. The other thing to note is that the photon ends touch, but they have no other reason to join. Now, to show its usefulness of this model, we'll use the fact that in 1925, Uhlenbeck and Goldschmidt discovered that electrons had a angular momentum of I omega equals half-hbar. Now, in a hoop situation, I is mass times r squared, and omega is c over r, because the photon is at the axis of the photon is always traveling at c. That gives that mr squared times, so if you then multiply both sides of I omega equals half-hbar by omega equals c over r, it gives mr squared times c squared over r squared equals h over 4 pi, which is your half-hbar times 4 pi c over lambda, which is c over r. Cancelling out gives hc over lambda equals h mu equals e. If we go back to the original one and cross off the r squared, you get e equals mc squared. So in this situation, it just shows that energy is the photon traveling at c linearly. Mass is the same photon rotating twice per wavelength. It gives the mass of a particle is just as h nu over c squared, and its radius is h bar over 2mc. As the earlier slide showed, space supports photons, so its space also supports all particles made from rotating photons. Now, I'd like to show you, the first thing we should work out is how do these photons move? Well, there's two possibilities are that it sort of rolls along along its motion direction, and the other one is that it moves perpendicularly. So it rotates this way and then moves perpendicularly to it. Now, I'm only going to consider B because it has been verified by observation. Now, if we're to look at that, we're just considering the axis at this stage. Look at the axis of a photon. Viewed end on, it's just a circle. Viewed obliquely, this is stationary rotating photon, it will just look like an ellipse. And when viewed side on, it's just moving up and down. Now, when the photon particle moves, viewed end on, again, it's still just seen like a circle, but viewed obliquely, it'll be seen to spiral its way through. And finally, when you viewed side on, it will just be like a stretched spring. Now, in all of these situations, the photon, or the axis of the photon, is traveling at c. Now, this makes it the hypotenuse of a right-angled triangle, and we can just apply Pythagoras' theorem. And I won't go through the full details. The math summaries are elsewhere, and I'll give them to you later. But one of the things I'd like to show, if you go through these, you finish up with that the radial velocity equals the rest velocity times the square root of 1 minus v squared over c squared. The radius, a particle's radius does decrease with its speed. And it'll be shown later, this has some very interesting consequences for particles. But it's only the radius that decreases, it's not the rest of space. The same calculations just give you the standard time, mass, and length corrections with increasing speed. Now, the other thing you should know that rotating photons are stable. Now, the spin of half-hbar is angular momentum, and it's the whole mass rotating at the speed of light. It's a powerful gyroscope. On top of that, with charged particles, they have a h-bar twist or spin, which is also angular momentum. The conservation of angular momentum makes those particles very stable. And another reason for them being stable will be given a bit later. It should also point out that in that derivation, the special relativity corrections apply only to photons. Only to particles. They do not apply to photons. Photons can only move at the speed of light, and whether it's traveling in a straight line or rotating, that axis is always at the speed of light. Now, as I said, in 1911, Einstein pointed out that photons had mass equals h nu over c squared. It has been measured many times. I'm at a loss why theoreticians keep ignoring it and try to pretend that they're massless particles. Now, just to illustrate a little bit more, here we have a situation. Let's just consider it as a particle. It's made 6 revolutions, basically traveling 3 wavelengths. Because this is always traveling at the speed of light, and this represents, say, a low keV electron, this would be like many MeV. The centers of the oscillations are wide apart, and the diameter is quite small because essentially the length in both cases is the same. I'd like to suggest that those last 3 slides show there is a unity between Einstein's special relativity corrections and the structure of matter. This structure automatically subjects all particles to the special relativity corrections. And it does also introduces that fourth correction of the reduction in radius as illustrated here with increased speed. And I respectfully suggest that that helps to justify my earlier comment on photons rotating perpendicular to their travel direction. Now, but what happens to the rest of the field? Well, if we consider circularly polarized photons, as I mentioned before, as was shown before, there will always be, each of the four fields will be in the one quadrant, in their own quadrant. So if you rotate it, say, in this direction, then in the first half cycle, you'll have the positive field on the outside, the negative field on the inside. The second half rotation, you'll still have the positive field on the outside. You'll have the south magnetic pole, in this case, pointing upwards in the in the first half, and the north pole pointing southward in the second half. But the north pole pointing south is the same as the south pole pointing north, and that's what gives that the magnetic fields reinforce each other. And what you've got, when the photons are traveling linearly, the magnetic fields are open. When they are rotating twice per wavelength, the magnetic fields form a closed loop. I'll show you that a little bit more. And that closed loop, it gives extra stability to circularly polarized rotating circularly polarized photons than it does to rotating plane polarized photons. Now, if we have a look at a case of a rotating plane polarized photons, then the polarities of the field swap. So it means in the first half of a plane polarized photon, we'll have, say, the positive field on the outside. In the second half, it'll have a negative field on the outside, so it will basically have no residual charge. The magnetic fields are in opposing directions. Therefore, they're not going to, if it's a Dirac particle, there will be no magnetic moment either. To visualize a rotating photon, we put an axis, say in this case, an axis off center, and if you just give that axis a twist, you'll get one field on the outside, the magnetic field pointing up, and the second field on the inside. And that gives you some indication what a particle would look like. Now, I'm going to give how is charge generated? And I'm showing here, this is a charge, positively charged Dirac particle. It's a positron. You have the axis of rotation of the photon. You have the magnetic field surrounding it. I've shown here that the electric field is in a plane. And this brings us to the origins of electric charge under this model. Now, the photon rotating at the speed of light at a very small diameter generates what you call a strong centripetal force. Secondary or virtual photons, you say, emitted or otherwise in the photons are the field particles of photons, and they're basically just thrown out. And they're virtual photons because if they don't interact with something else, they'll just be reabsorbed for conservation of mass purposes. Now, under QED theory, electric charge is caused by the emission and absorption of virtual photons. In this case, they'll be emitted at the plane or at the circumference of the rotating photon and in its plane. And its charge, the photons will spread out away from that plane as the photons, virtual, real, move away. So electric charge, in this model, electric charge is emitted at the circumference. It's a planar structure, so it is two-dimensional at its origin. Now, to some, this may seem a little different, but I'll show you later on. It has been observed to an accuracy of 0.01 FM, which in my thinking is reasonably accurate. Now, this origin shows up when, as I take an electron and positron annihilating each other. When they are rotating photons, they have opposite electric charge. They both have electric charge, even though it's opposite. When they unlock each other's angular momentum and become linear photons, their charge disappears. Yes, it can be postulated mathematically, but mathematics doesn't make things happen. Physics makes things happen. And that is the physical reason why it happens. Then we come to polarities of charge. Well, in this particular, you saw in the earlier couple of slides back that the electric field and the electric field is perpendicular to the magnetic field. And if you have a case, and I'm saying if you've got left-handed chirality, as shown here, the North Pole points out of the page, the photon rotates clockwise, and I'm using that as suggesting that that is negatively charged. On the other hand, right-handed polarity gives the North Pole pointing out, the photons rotates anti-clockwise, and I'm suggesting right-handed chirality gives positive charge. Now here we have 4 illustrations of what could be regarded as the same photon, photon with the same properties. Now there are only 2 ways it can rotate, clockwise, anti-clockwise or clockwise, and the spin of the photons can only spin one way or the other. So there are only a total of 4 combinations available. So here we see photon rotating anti-clockwise with the North Pole pointing out. Here we see the same photon rotating clockwise, and there the South Pole is pointing into the page. They are both positive charge, and with the south with the North Pole pointing out of the page and the photon rotating clockwise, you have a negative particle. And the same thing with the reverse, when the South Pole is pointing out, the North Pole is pointing in, the direction of the electron flow is anti-clockwise, and again, it will generate a negative charge. So that what you have is a situation where the one rotation, or the two different rotation directions just define the spin of the particle. And here, if you look at A, you'll see that's a mirror image of D. You'll see they're both moving up that way in the middle, and both North Pole, they're mirror images of each other, and mirror images of each other makes them antiparticles. Now, it's been known for a long time that antiparticles are a mirror image of particles, and this is one of those reasons. Well, this is a physical reason. The different states of spin are determined purely by the direction which you look at it. I mean, a spin-up particle, if you use that as this case, is just an opposite side of the page image of a spin-down particle. No other spin or chirality states are possible. They are the only options you've got. I'd like to just show a brief statement on how this works. Consider we've got 2 observers. You've got a photon rotating clockwise. In zone A, both observers will see it rotating clockwise. In zone B, between the 2 observers, observer 1 would see it rotating anti-clockwise, while observer 2 will still see it rotating clockwise. And in zone 3, both observers will see it rotating anti-clockwise. even though it's continuing to rotate in the same direction. So just use that as just a further illustration that spin is just the other side of the page image of the same particle. That also brings us to the case of what happens when particles become entangled. Well, you take this situation when two electrons get close enough to become entangled, the only possibility you have is that the north pole of one is attracted to the south pole of the other, and they'll just stay that way. Now, the only way you can break that entanglement is to apply h-bar twist to one of them. That turns the whole half h-bar, goes from plus half h-bar to minus half h-bar. And that breaks, that's the only way you'll break the entanglement. And then they can go off you can take them, let them go off as far as you like. And as long as you don't change the spins, then they'll always be, if they are entangled, they'll always be measured as having opposing spins. The other one of interest is the de Broglie wavelength. I mean, the thing about this particular model is that everything has a frequency. The energy of rest mass energy of a particle is m0 c squared equals h times its rest frequency. Its frequency at when it has energy EV, its frequency change from nu0 to nu v, and given by the relationship that EV squared plus P squared C squared equals m0 squared C to the fourth. The KE is PC equals H nu KE. You can just go directly from there to here. PC equals HC over lambda KE, gives lambda KE equals H over P, which gives you the de Broglie wavelength. Now, while that's a mathematical description, which I said I would give the physics first, I'm just doing it in that way so you can hopefully understand what's happening physically a little bit better. Consider the case of an electron is just moving along through space. It's moving perpendicularly to its rotation is perpendicular to its direction of travel. And this shows rather crudely the fact that there will be a very high frequency oscillation which generated for an electron is about 10 to the 20 hertz, which is fairly high. Now, for those who studied Feynman will know that high frequency electric field oscillations generate disturbances in the electric field. So the only disturbance that can be is electromagnetic. And the previous calculation showed, therefore, the only possible outcome. I suggest that what it is that the wave starts out as the influence of the oscillations disappear in either direction. The wave starts out weak, goes to a maximum where the particle is, and then diminishes back to nothing again. That particular wave, of course, is traveling at c, and it's just like any other electromagnetic wave. Now, to give you perhaps a bit of an appreciation, if the electron is moving slower, it has had longer to influence the field around it, so the wavelength, the influence will be greater and the wavelength will be longer. So just give a quick summary here of the properties that all particles will have that are constituted of, well, every individual particle consists of a photon making 2 revolutions per wavelength. That gives its mass, its radius, its Bohr magneton. Now this is, I haven't calculated this is measured. In E equals mc squared, energy is a linear photon, mass is the same photon rotating twice per wavelength. Particles are automatically subjected to special relativity corrections when they move. Spin is angular momentum as first proposed, and that angular momentum is half h-bar, and it is the mass of the photon making 2 revolutions per wavelength. There are only two states of spin possible. Both states exist at the same time. The direction from which they are viewed determines the measured value. All individual charged particles, the photon of all individual charged particles has an intrinsic spin or photon spin of h-bar. Charge is generated at the rotating photon's circumferential axis basically because of its angular momentum. It is two-dimensional in origin. The angular momentum is the same, and therefore charge will be the same for all particles. Neutral particles have a plus half and minus half charge. The magnetic field is perpendicular to that plane. Particle's charge is determined by the photon's rotational chirality with respect to its magnetic field. An antiparticle is a mirror image of a particle. Different spins are just other sides of the page image of the same particle. As the particles move through space, their magnetic field leads, and they automatically generate the particle's de Broglie wavelength. Rotating photons have oscillating electric fields. That is the cause of the electron zitterbewegung, and all other particles have equivalent oscillations. Now I'd like to briefly go through some of the particles. Now these are the standard well-known properties for an electron, but it has additional properties. The frequency of the oscillation is about 1 times 10 to the 20. It gives it a radius of 193 FM. And this is just a reverse of the positron shown earlier. You've got the electric field rotating in one direction, generating charge. You have the magnetic field, and the charge just spreads out from the axis as the photons get further away. Now, think about when this moves, the rotating axis will actually spiral its way through space. Now, that has led to what's called, some people call it helical Mott scattering, where they believe they've detected the charge of an electron spiraling through space. Well, I respectfully suggest that that's just because that's what happened when an electron moves. But electrons do have some awkward properties that have made them difficult to understand. The first, of course, they display nanometer dimensions at a few EV. As shown earlier, this is just the de Broglie wavelength. Near rest mass, it's been known from other particles that magnetic moment is charge times radius. It's EH over 2mc suggests its radius is somewhat around this value. And yet at the same time, when it's accelerated to T, the energy just has a scattering cross-section of about 10 to the minus 18 meters. So you've got a difference of 10 to the 9th in a particle's detected structure. That's been difficult because that low scattering cross-section is just this special relativity corrections as mentioned earlier. And I respectfully suggest that this rotating photon model explains them all and throws in the special relativity corrections and the Broglie wavelength for good measure. But it has some other awkward properties. One of them is interference. Well, fairly straightforward. You have two slits. The de Broglie wave is an electromagnetic wave. It will just pass through, and the waves will interfere if there's no disturbance. The waves just interfere in the normal manner, and it really doesn't make any difference which slot the electron passes through. It'll gather in along the greater strength, and if you have enough of them, you'll get your interference pattern. But what happens when you try to measure through which slit the electron passes? Well, in order to do that, you have to place a sensor over one of them, which usually includes a voltage. Now, placing a voltage over one and not over another will put the phases of the electromagnetic, the same electromagnetic wave, just put them out of phase, you won't get an interference pattern. If you put voltages on both of them that are exactly the same, you will, well, the waves may be the same. By the time the electron goes through one of them, it will disturb the waves through the one through which it passes. So again, you won't get an interference pattern. Another one, of course, is tunneling. And the well-known effect is that you have an electron approaching a barrier. It hasn't got enough energy to overcome it. Its de Broglie wave can be long enough that it can appear on the other side. You have the possibility, the electron can appear anywhere on that wave, according to the standard theory, and therefore it has a possibility of being able to penetrate or tunnel through. But there's possibly a particle explanation. And this is just referred to the good old billiard ball trick where you set up a group of billiard balls. One comes along, it hits, transfers momentum all the way through, and the end billiard ball drops out. Well, electrons are in a complex taut field, and they're attracted by protons, repelled by other electrons. They basically respond to every stimulus. So you have an electron coming along that will hit into a target and transfer momentum through the barrier. And if at the end an electron has sufficient energy to overcome the work function between the two surfaces, it'll pop out the other end. Now, I just suggest that there is a way of distinguishing between the two, that lower energy electrons have longer wavelength and therefore greater probability of tunneling, and higher electrons have larger momentum, and that would give them greater probability of an electron emerging out the other end. I don't think that's a very difficult experiment to try. Next, we come to photons. They've got all of these, the usual list of properties, charge, but the magnetic moment is beyond the charge times radius situation. Its frequencies are these values times 10 to the 23 hertz, and its radius is 0.1052 FM. Now, we're in the fortunate position that the charge distribution on photons has been measured, and was done by Hofstadter and his team in the 50s. If all of the charge was at this dimension, then it would have this magnetic moment, and you would have all of the charge at this point, which is very close to 0.1052 FM. If it was measured experimentally, you call it experimental limitations, would mean you wouldn't measure it as a single point. You'll get a bit of an exponential decay. It's shown there. What is actually measured is this curve 2. It peaks, yes, about 0.105, just about 0.1 FM. Now, I suggest that that is a very good indication that charge is generated, or the charge generated by this mechanism has been detected to an accuracy of about 0.01 FM, because it's pretty close to, within 1/10 of that distance. Curve 3 is just part of the way between these two. It really doesn't mean anything. But the important thing out of this is that there is something within a proton that's spreading its charge. Instead of being here, it's spread out here, and it's increasing its magnetic moment. So we now investigate what that could be. Well, there's a couple of possibilities. One is that the wavelength, which is the black one here. The wavelength is non-sinusoidal. Now the black curve is just a sine wave. The blue curve is if it had a 1/3 frequency harmonic imposed upon it, then it would get the red curve. Now, why 1/3 frequency harmonics? Well, this is a plot in what you'd call a momentum space. Whenever there's a regular disturbance, a 1/3 frequency, where the disturbance drops that down, the 1/3 frequency goes up. And anybody who's ever talked to radio engineers knows that getting rid of 1/3 frequency harmonics is a real problem with radio waves. Now, if that is made to rotate, what you'll get the main oscillation, and then you'll get an oscillation of 1/3 the frequency, which will be 3 times the wavelength. Now, the other possibility is that the centripetal force on a proton, it's huge. I mean, it's the whole mass of the proton, which is nearly 2,000 times that of the electron, rotating in a radius about 1/2000th that of the electron. I mean, it's just, everything goes everywhere. What will happen is that then you'll get these very large photons massive photons being thrown off, and they will have the 1/3 frequency harmonics. So this is just gives a situation where you have the main 1/3 main, what I call a P/1 oscillation, that's generated 3 P/3 oscillations. Its spin is conserved, mass is conserved, but they're all positive. So charge isn't conserved. So with the equal probability of that occurring, you would have the probability of 2 negative charges and 1 positive charge, which would then give you a total. Out of the 6, you would have 4 positive and 2 negative, which gives you an average of 2 positive P/3 oscillations and 1 negative P/3 oscillation. Now, here's just a quick indication of the different properties of the primary P/3 and P/9. The thing about P/9, as the frequency diminishes, the radius increases, the magnetic moment increases. One's worth having a quick look at here is the mass of a P/9 oscillation, 104.25. 105.6, not much different. More on that later. These are the proportions that you need to finish up getting the protons' observed magnetic moment and charge distribution. So it is suggested that these harmonics are actually spreading out your charge and increasing the magnetic moment. Now, these oscillations will just pop into and out of existence as required for conservation principles. And while this may seem a little different, they have all been detected. So let's take the P/1 one, 0.105 FM. That looks like a pretty good detection there. The P/3, 2 positive, 1 negative, near the proton center. That remind anybody of something? Quarks, perhaps? Or are they quarks? Or are they just 1/3 rotating harmonics? And the P/9, well, yes, it's, as I'll show you later on, it's got almost exactly the same properties as a muon. The only difference is that in the proton, it's bound, so its mass is just a little bit less than when it's free. Here's a few ways of representing a proton. Here we have just a plan view of the charge. The rings just merely indicate the intensity of the charge as best I can. This one you've seen. This one is just that doubled up because its charge is distributed all around. Here it's like an oblique view of the distribution of charge. Its height is charge, not physical position. This one, as the previous ones, where it just shows the whole thing is embedded in a positive field. And here you have this charge plane viewed obliquely and a magnetic field surrounding it. The whole thing to note about this is everything is electromagnetic. Nothing is solid mass. If we come to neutrons, again, the same sort of properties you're already familiar with. Think about it, it's zero charge, but it has a negative magnetic moment. And the properties of the rotating photon are pretty much the same as that of a proton. This shows the charge distribution of the neutron. It starts out positive, which I'll show here is the positive core. It then goes negative, and for the same reason that the proton had two positive and one negative, the neutron, because this oscillation is negative, will have two negative and one positive. It then goes positive, which are these P/3 oscillation, P/9 oscillations, which are the same as a proton. But in order to match this very high magnetic moment, you need the N/27 oscillations. Now, here's a table. This just shows the properties of the various harmonics. The N/1 is positive, N/3 is negative, N/9 positive, N/27 negative. And these are the proportions that are needed, and that finishes up to match the neutrons' observed magnetic moment and charge distribution. One thing that's worth looking at is the mass of the N/27 oscillation. 34.8, and the bound muon 104.4. 109 MeV per c squared is looking pretty good, isn't it? Now, again, here are various representations of the neutron. It's oblique charge, and the one I like, the positive central core, negative P/3, negative N/3, positive N/9 oscillations, and finally very large negative N/3. Next, we come to a neutrino. Usual property, organic properties, spin half-hbar, no charge, no magnetic moment, and an upper mass of 0.1 eV per c squared. Here I've just done a schematic illustration. A neutron decays to a proton plus an electron plus. Now you've got charge 0 going to plus E, minus E, zero. Spin goes from plus h-bar, gives plus h-bar, which is one h-bar too many, and therefore you have to have a spin minus half h-bar. All other things are conserved. The standard model treats neutrinos as point particles with properties attached. Under this model, a neutrino is a Dirac particle composed of a rotating plane polarized photons. And when neutrons decay to protons, it's just a rearrangement of electromagnetic oscillations with all factors conserved. I mean, not like in the standard model. How do quarks and gluons decay to give an electron and a muon when the quarks are supposed to be elementary particles? This one's just straightforward. But, you see a mass of 10 to the minus EV per c squared. Why is it so small? Well, you've got three possibilities. The time when a neutron, neutrons have a half-life is what, 12, 15 minutes, somewhere around there. by the time it actually starts to decay, the decay process gives it a rest mass. It takes place in about 10 to the minus 10 seconds. That gives it a rest mass of approximately 10 to the minus 4 eV per c squared. Also, the time for a neutrino to arrive after photons from supernova, again, they're within a few seconds. Now, if we do the reverse of the corrections, relativistic velocity corrections, you get that mv over m naught squared. In order to travel tens of thousands of light years and be just a short time behind a photon, you need that rest mass of about 10 to the minus 4 eV per c squared. And then finally have these results by Bernardini, which suggest that the maximum flux of neutrinos is again about 10 to the minus 3, so about 10 to the minus 4 eV per c squared. So it just suggests that all of those put together, yes, the photon, but the neutrino has a rest mass of about 10 to the minus 4 eV per c squared. Now to have a quick look at what that means. First of all, cosmological neutrinos have a wavelength of about 20 millimeters and a radius roughly of 2 millimeters. And that is why their large radius is why their small mass can still have half-hbar angular momentum. Now, the neutrino radius of 2 millimeters makes them by far the universe's strongest gyroscope. I mean, it's very difficult. They just travel. It's very difficult for them to change their direction of travel. They can only be absorbed when if their leading structure strikes a receptive nucleus in exactly the right position. I mean, electrons have no way they can absorb a neutrino. A 0.01 eV neutrino has a speed of about 0.99 c. And that's why 0.01 EV is a very low energy neutrino, but that is why neutrinos are all detected as traveling basically at the speed of light. The rest mass gives them a temperature of about 1.7, or temperature equivalent, about 1.7 degrees K. So that although rotating plane polarized photons are not stable, there's just no lower energy to which the neutrino can decay. That's what it is. Another particular property, a neutrino radius decreases with increasing energy, just the same as I showed earlier. A 1 GeV neutrino has about the same radius as a nucleon's central core. And that's why higher energy neutrinos are easier to detect, because they're about the same size as the neutrons that can, as the nucleons and nuclei that can detect them. So I respectfully suggest that under this rotating photon model, neutrons are not difficult to understand. Their low frequency, or their low mass, high angular momentum for mass, zero charge, zero magnetic moment just really make them difficult to stop. Now we come to elementary particles. Now the first thing to realize about elementary particles is Einstein's special relativity corrections. Mass increases and time slows down when particles travel at a high speed. Now from there, they're quite stable at that. I mean, GeV cosmic rays travel for tens of thousands of years without decaying. But when they stop, they have excess mass for their new rest time. They've got to get rid of it. Now they can do that by emitting linear photons, which we all know as Bremsstrahlung. And the other thing is that these outer p/9 oscillations can just be jolted out. And here I'm just showing that their properties are just the same as a muon. As I said, their muon's mass is a bit higher because inside the nucleus, the particles are bound, so they lose a bit of their mass to that binding out, and they pick that up when they're free. But when you jolt a positive muon out of a proton, it converts it to a neutron. Now, as we know, when a proton decays to a neutron, it generates an n/27 oscillation, and that has a mass at 34.8 MeV. So combining the 105.6 with 138, you get with 34, you get about 139 MeV per c squared. Now, and then 27 oscillations can be negative, neutral, and positive. I mean, you've got to have everything going on when the atoms collide, when the nucleons collide with each other at very high energies. If a neutral 27 attaches itself to a charged muon, there's not much binding energy there, so the mass stays at around about 139 MeV per c squared. It has spin 0 or 1, and it decays to a muon plus whatever else. But when you have opposite charges, you have a positive attaching to a negative. It will give some binding energy. That drops the mass from 139 MeV to about 135 MeV per c squared. And the similar dimensions means that the two, the radii only differs by a factor of 3, so the two can actually sometimes release each other's angular momentum, in which case they will decay to photons as well as decaying to muons, as shown here. So because pions are by far the most common particles emitted in proton collisions. And energetic protons, they just keep replacing the lost oscillations until they reach a stable state. Now, in doing that, all they do is just cascade through a series of quasi-stable particles emitting pions and protons as appropriate until they reach a stable nucleus rest mass, stable nucleon rest mass. I won't pronounce these particles, but these are just the final stages of decay. This particle generates that plus a pion, this one, that plus a pion, a pi, neutron plus a pion, and they're all generating pions. And what they respectively suggest, these are not separate particles. They are simply the final stages of nucleons cascading to a stable rest state. The situation with higher energy nucleons is more complex, but not fundamentally different. Higher energy particles can form more combinations with greater complexity, making them more difficult to understand. But are they really anything more than just adding mass to nucleons, the removal of which gives structures that aren't present in them at rest? Well, if there is something more, it should show up in the way nucleons bind to form nuclei. So I'll now give you a quick introduction to that. Just as a reminder, here are what the representations of the nucleons that I'll use: proton and neutron. Explained those before. Again, these circles just represent intensity of charge, not rotating photons. So what happens when a proton comes close to a neutron? Well, here we've got two situations, one of 5 FM spacing and one of 2.5 FM. The first thing to note, because charge is generated in a plane, they will align themselves in a planar array. Here at 5 FM, you'll see there's just a tiny bit of overlap of the neutrons n/27 with the protons p/9. There will be, if their spins are the same, there will be a bit of a magnetic loop between them. But at 5 FM separation, there isn't enough overlap to give any form of binding. However, the situation changes. At 2.5 FM, I mean, the magnetic binding is virtually r-cubed, so the magnetic binding will be about eight times that at this distance, And you're starting to get some of the protons p/9 operate overlapping the neutrons n/3. That will give a particle with 2-h-bar. It'll have spin +1 because they're both spinning in the same direction, and its magnetic moment will be the difference between the two. So that suggests that there is some magnetic binding when the charges overlap. So what I want to do now is just take you through the different stages as the protons, or as the neutron gets closer to a proton. Now 3 FM, there's not much overlapping, but you see here at 2.5 FM, there is starting to be significant overlap between the p/9 and the neutrons (n/3). Now, overlap means that charges, because they're rotating photons, they're overlapping. They are overlapping at essentially zero distance. And you can consider this sort of binding division by zero electric attraction. I mean, after all, plus 0.1 E overlapping at minus 0.1 E at 0.1 FM has the same force as a plus E overlapping a minus E, or close to a minus E, separated by 1 FM. So it is a strong force. The shorter distance also increases magnetic binding. And the closer you get, of course, the more the overlap, the stronger the binding, until you get to about 1.2 FM. That's about as strong as it gets. And now you've got the two charges starting to overlap, two positive charges starting to overlap. By 1 FM, it's quite a strong overlap. At 0.5 FM, it's a huge overlap. I respectfully suggest that shows up in this work by Cook. It shows the relative binding strength versus distance, and starting out 3, 4, 3, 2, about 1.2, it's about the strongest, and suddenly it becomes very, very strongly repulsive. And I suggest that's the reason why. Next, we have a quick look at what happens with neutrons at different center-to-center spacings. Really, a bit of binding, perhaps, maybe, until you get to about 1 FM. And then the negative n/3 oscillations are really strongly overlapping each other. And that's why you really can't get neutrons much closer to each other than about 1 FM. Now, to give an indication of how this works here, we'll consider these A = 3. The two, first case, you have 3H or tritium. Two nucleons have opposing spins, so that they will add magnetic binding. They both there's a tiny bit of overlap of the p/9 with the n/3, but not much. These two can, well, there's no repulsion between the neutrons, so they can move in close to the proton, and that well, first of all, because the neutrons are reverse spin, the residual magnetic moment will be very close to that of a proton, and it'll have a spin half. Because there's no repulsion to the neutrons, they can move a little bit closer. So the proton to neutron binding energy is, well, it's been measured, 4.2. Total binding energy divided by 2 is 4.24 MeV average. The separation centered about 1.6 FM. We now go to 3H, 3He. The two protons have different spins so that they can get some magnetic binding to each other. One of them is bound to the neutron. one of them will have some magnetic binding, the other one won't. The protons will try to push each other as far away apart, and that's why the distances are a bit further apart, and they have a slightly weaker binding energy per proton-neutron bond. And they will have these spins cancel out, so they'll have again a residual spin of half h bar, and their magnetic moment will essentially be that of the residual neutron, which is of course what is observed. Going to 4He alpha particle. The protons, as it shows all the fields imposed upon each other, the protons will try and get as far away from each other as possible, and the neutrons will be drawn in as much as possible. Like this may be hidden by, but what you will have is that the spins of the equivalent, proton will have one proton spin up, the other one spin down, one neutron spin up, one neutron spin down to get maximum magnetic binding. To finish up with a particle, no magnetic binding, and 28.28 EV binding energy. It's a very they're very strongly bound, 7.07 MeV per c squared at a distance of about 1.2 FM. What we can now do, we've got several points that we know, and we just plot these in terms of binding energy that way in MeV versus proton to neutron center to center distances here. That's 4He, tritium, 3He, deuteron, and the overlap between the N26 oscillations and the protons neutrons N/26 and the protons P/3. It stops at around about 5.5, 6, somewhere around there. I'm not exactly sure when, but that's the reason why the strong nuclear force ends about there. The other reason, why can't a helium, why can't we have a = 5? Well, the proton can immerse itself in neutrons, one of the neutrons, N/27, but they don't last very long, so it won't stay there. And the same thing, a neutron can put its N27 over one of the protons, but they don't last very long. So A = 5 nucleons are not stable. Okay, now we go through some nuclear binding rules. I'm not going to read these out to you. I just like to show you they exist, and they're not very complicated. But to show them, you have consider the possibilities of lithium nuclei. You have two possibilities. You have an alpha particle with a deuteron superimposed on it. Well, the only other possibility is the three protons as far away from each other as possible and held together by the neutrons. It's hidden behind here, but there's an Li7. It's just putting a neutron in there. The Li7 is actually the largest nucleus that can form in a single layer. I mean, you can tell the difference between these. If it was this structure, the charge density of a lithium nucleus would be similar to that of an alpha particle. If not, the alpha particle has got the strongest charge density, and lithium has the weakest charge density because that's one where the protons are furthest apart. The other one to look at, carbon nucleus. As has been proposed that there could be 3 alpha particles somehow joined. Yes, it could be that with the appropriate alignment of magnetic fields, but that would give the two things. It doesn't give anywhere for carbon to have any isotopes, and it also make the carbon a very strong charge density. So the only other possibility is 2 of these equilateral triangular states superimposed upon each other. Now, a few years ago, somebody experimentalists are pretty good, and they did these measurements and they found out that yes, indeed, the structure of a carbon nucleus was an equilateral prism structure. So this structure has been observed. So I guess we're on the right track to showing that this model does work. Just like to quickly go through, there are a lot of higher atomic number nuclei which we need to consider as well. And under the rules of binding, these are the structures that can form in a particular layer. First thing to note, they are not circular. Second thing to note, two protons, 2 neutrons, 6 protons, 9 neutrons, 9 protons, 14 neutrons, 17 protons, 27 neutrons. You need, in order to fit in this structure, you need more neutrons. As the number of protons increases, you need more neutrons to bind them. The other thing to note, if you have a look at each one of these nucleons is in at least one alpha particle structure. And that's why it's so easy to knock alpha particles out of nuclei by giving them a bit of a hit with something. These are some of the, not all of these neutron lattice positions have to be filled all the time. And these are some of the layer structures that exist when neutron vacancies exist. The binding between, within a layer, you have that strong electric and magnetic binding that I mentioned earlier. The binding between layers is just a result of the residual magnetic field. Now, one thing about these two structures is that most nuclei, as long as they're assembled according to, most nuclei that are assembled with using these structures are either stable or will have a half-life of a few seconds. We'll get more into that later. To give you an indication of just this at work, here between 24 AL and 30 AL, you have the limits of isotopes under this structure, and you'll see the lowest number 2 seconds, the highest number 3 seconds. The most abundant isotope, Al27, has one of its neutron lattice vacancy positions filled, and the reason for that is that an even number of neutrons gives stronger binding than an odd number of neutrons, just because there's one extra loop formed. Again, if you just add, add protons, add neutrons, yes, well, I can't say it. You add neutrons and you get unstable, because a neutron can attach itself by its N27 to any external proton, but because the oscillation doesn't last that long, it's not a very stable bonding. Here again, showing removing one neutron below that one second neutron, the half-life diminish. And showing here where some neutrons have been attached to some protons, as mentioned earlier, half-life is quite low. Now, for those who are really keen, what you can do is you can work out the spins, the orientations that's required to get maximum magnetic binding. Then you finish up, when you do that, you'll find that you have a spin of 2.5 or 5/2. If you add up the magnetic moments, you should get a value of 4.55 mu BP, but it's actually been measured at 3.64. The difference is just due to a slight compression of rotating photons during their overlap process. But otherwise, that's all. I want to just show you quickly oxygen. Just a couple of other examples. You have oxygen. Its most abundant isotope has 2 He there, and these two neutron lattice positions are not filled. The rest of it, again, you can attach protons to, you can attach neutrons to external protons, but the more you attach, the smaller, the shorter the half-life. Calcium is an interesting one. Two reasons. First of all, it's the most abundant isotope. Has all of its neutron lattice positions vacant in this 6-layered structure. And there we go through, as you go up, that's just like oxygen has, calcium has, and that's all of the even Z numbers above 6 and above are in that position. But when you get to 48 Ca, which is still a stable isotope, you've filled, in this position, you've filled all of the neutron lattice vacancies at 46. So the only way that this can be stable is that you have to have a rearrangement of the number of layers in the nucleus. And in this case, calcium 40 has 4 layers, not the 6 layers of the previous ones. Now, the reason I mention this is that when you get to higher Z, you know, around 40, 50, 60, and that sort of thing, you can get many different isotopes. The same isotope of a particular element can have different structures. And it is the structure that determines the stability of the nucleus. And basically, if you have the strong nuclear binding consists of overlapping charges which appear and disappear. Well, if the arrangements of overlapping charges is different, then some can disappear faster than others. And that's the reason why you have at higher Zs, you can have the two isotopes having the one isotope having 2 different half-lives. Anyway, let's move on. What I want to show you, one of the problems that bothered nuclear physicists for a long time is what's called the nuclear skin effect. Now it's shown here, I'll show it here with, let's just say, gold and bismuth. It's the charge diminishes it's a distance of the charge diminishes from 90%, which in these 2 cases is about 5.5 FM, to about 10%, which is around about 2 FM. So that's about 2.5 FM. Now, if you have a look at this curve here, you'll see that, yes, starting out 0.1, it's still dropping at about at 2 FM. Allowing that these nuclei are pseudo-spherical so that you'll get some charge diminution. And they're not cylinders, they have a bit of a curved shape, and allowing for that curved shape. What you're doing is measuring this charge distribution, and that goes along with what I said very early on when I derived the special relativity corrections. The nucleus, or all nucleons, in fact, all particles move with their the charge plane rotating in this direction, they move in this direction. So what you're seeing here in this skin effect is all of these charges superimposed upon each other and the electrons coming down from the top scattering from them. So the skin effect really just shows that, yes, nucleons or all particles, when they move, orient their spins so that they present the charge plane in perpendicular. The charge plane is perpendicular to their direction of motion. Another one that's perhaps worth a quick look at, I'll show here, carbon and oxygen. You'll find there that they go to a maximum and then they just dip down a bit. Now, if you have a look here at the carbon structure, you've got 3, because remember, it has a an equilateral, a prism equilateral triangular shape. You have these two layers on top of each other, all the charges on the outside. So electrons coming down scatter mostly on the outside and somewhat less on the inside. Oxygen is exactly the same thing. You have, but there you have three layers with charges on the outside and virtually nothing in the middle. Electrons scattering out of oxygen have to come back from three layers. So that depth drops off a bit. I respectfully suggest that this is strong proof of the correctness of the model, but the charges, the particles do move always with their charge plane, shown here, perpendicular to their motion direction. Well, helium has the very, very high core density because this is as close as you can get. It's the only two proton structure where both protons are pulled in quite strongly. Just like to prickly measure, I mentioned something about lead. PB82, it's got all of its neutron lattice positions vacant and all its stable isotopes are lower mass. Excluding PB209, which is also stable if you regard, stable. All other nuclei with higher Z first of all, I'll have all, the most stable one will have all of the most abundant. Because of this, you won't find any higher. You won't find any higher atomic number or mass number isotope than these that are stable. There's no such thing as magic numbers. As I mentioned before, neutrons can attach to external protons. But by the time there's about 10 of them in most cases, the half-life became really short. And there has been attempts to determine the neutron drip line by smashing larger nuclei together and measuring what comes out. But in order to get the high number they give with sodium, you do need a bit of magnetic binding only, and those isotopes are very, very short-lived. And they're doing that so they can learn something about the structure of nuclei. And I respectfully suggest that if they use this model, they'll get a lot further than they will the way they're currently heading. Just as a quick one. The two dotted lines represent the limits of which the most abundant and stable nuclei with half-lives above seconds or two are found. And you can, they've got thousands of nuclei, and this works exceedingly well with just a tiny bit up here where it goes outside, and I haven't modified the theory yet. The other thing is the most abundant nuclei start out at less than 20 at the minimum A for Z. It reaches a maximum A for Z. It's certainly there by 82. I don't know exactly when it gets there. The most stable isotopes gradually change from one to the other, and when you get to tin is about 52. It's not quite in the middle of this, but it's got the most number of isotopes, with the less abundant ones on the lower, more isotopes. There's 50 more isotopes below the most abundant line than above it. I'd like to very, very briefly go on to, because of the interest in uranium, it's U-238, again, all neutron lattice positions filled, 235, and got neutron vacancies, as you would expect. The interest of the uranium is in fission, so I just want to show you quickly what's happening there. This is the same U-235 as shown before. It's an 8-layered structure. So you've got the middle down here. The line H, that is where a fracture plane only has to break 4 proton to neutron bonds in this situation. So if it fissions, if it splits along that line and this layer attaches to the upper layer, it'll give an atomic number, I haven't taken off the extra neutrons, but it'll give an atomic number of 134, and the bottom one will be left with an atomic number of 101. If we go and have a look at, these are the mass number of fission fragments and presented by Weil. Well, 101 near the top, 134 pretty close to near the top. The chances of splitting, but if for example, we just split off here, this little section here, and it went with the bottom and the remainder stayed with the top, you would get the top one would have 161 and the bottom one would have 74. And you show here 74, yeah, not bad. 161, well, we've got to take off a neutron or two. You can take them off whenever you like, but I respectfully suggest that this particular model is rather good at also explaining what is happening with uranium's fission. Now, just briefly run through models with when nucleons bind. First of all, they completely retain their structural integrity. There's no quark, gluon soup or anything like that. The strong force is a combination of the opposing charges overlapping at essentially zero distance and the magnetic fields oriented to give maximum magnetic binding. Nuclei with Z greater than 3 all form in multiple layers. The layers are held together by the residual magnetic field, and it's probably less than, it's around about 20% or less than the binding per nucleon in the within each plane. So the electrons required to hold photons together increases faster at a rate that in this lattice. Allows us 208 and 209 PB and BI respectively are the highest A and Z stable nuclei. You can search as much as you can get funds for, but you will not find any higher magic number nuclei that are stable. This model allows the structure and some properties of any nucleus of any A and Z to be calculated to either match observed properties or predict new ones if you're looking for them. The nuclear skin effect is just due to the way the proton's charge distribution is being measured because of the way they move. They always move exposing their spread out charge. The spin of a nucleus is the sum of the individual nucleons. Nuclei do not spin. The magnetic moment of the nucleus is the sum of the moments of the individual nucleons with a slight rotation, slight rotating photon distortion, just because the charges overlap. The transient nature of the rotating photon harmonics, in that they pop into and out of existence, means that the strong force periodically fails. That depends upon the structure, and then radioactive decay follows as just the harmonics are rearranged. I respectfully suggest that this model's success in matching nuclear structures and properties leaves little room for further modification by a better understanding of the 200 plus elementary particles that have been detected, muons and pions excluded. But just to finish off, you can't really start building the universe around you until such time as you put electrons around nuclei. I mean, our standard model was that, classical physics, the electron spirals around, emits photons as it does to change direction, spirals into the nucleus, and the latest calculation suggested that would be happen in about 10 to the minus 12 seconds. It doesn't happen. So in order to overcome that, it was postulated that orbits are quantized. and they were quantized, depending on which books you read. They're fixed orbits follow fixed de Broglie wavelengths or integers of angular momentum. The orbits don't include the nucleus, and because they're fixed, they don't have to emit photons to change their direction. The nucleus won't collapse, problem solved. Yes, well, maybe. But the reality, under this model, electrons are larger. The diameter of a rest electron at rest is 386 FM. That of even the largest uranium nucleus is only about 20 FM. I mean, it just won't fit. You can't put it there. And even if you could, naturally occurring don't have any gap to accept them, so atoms won't collapse. But that doesn't answer why electrons have fixed binding energies, and which have been interpreted as quantized orbits. Well, obviously the 1s1 orbit binding energy is really well fixed. It's Rydberg's equation, and there's the calculated values, the measured values, 122.45, yeah, not so bad. So when 306.1, it starts to get a bit worse as you go down the as the atomic number increases, but otherwise not so bad. But what about the 1s2 electron? Well, the first thing to realize is there is only a fixed number of protons within a nucleus, and each electron that's in there, say the 1s1 electron, screens out the effect of one proton. So the binding energy of a 1s2 electron is basically the 1s1 electron minus some function of screening. Well, I suggest that this is one equation that is a screening, just one screening equation. If you haven't worked out, all values are expressed in electron volts. I'm a physicist, not a chemist. I don't understand kcals per mole very well. Anyway, unfortunately, the table is a bit hidden, but these are the calculated. We see here 7478, 7481, 648, 6847, 6851. The binding energies due to this screening function are quite closely match what has been observed. Now, doing it just for one is not good, so I've done it for 2s1, 2s2, 2p1, 2p2 as well. And again, the same. Here are some suitable equations. The calculated values, which are in the normal print, are calculated from the experimentally measured values, which were the previous lot. And go through again: 190.4, 185, 618.8, 611.2. 1571, 1570. Yeah, it's reasonable. It's a little bit better than what was obtained from the Rydberg constant, Rydberg equation by the time you got down to here. Same thing with 2s1, 2s2, 400, 398, 1218, 1213, 1634. And they've done the same 2p1, 211, 208, 480, 479, 754, 756, and so on, including the 2p2 ones, 1250, 1260, 1392. So all I'm suggesting out of this is that the orbits are not quantized because of the Broglie wavelength or angular momentum. It's just that there are a fixed number of protons in a nucleus, and screen out but it doesn't answer. There's still other questions to be answered, and one of them is, or a couple of them, So how do electrons move in atoms, and why do they pair? Well, they don't move, they certainly don't move in neat orbits. This model supports a suggestion made by Berry a couple of decades ago. They move more like pairs of electrons subject to some restriction. In their motion, they can just traverse across an atom about 10 to the 14 to 10 to the 16 times per second. They exchange photons with the nucleus to keep within the nuclear potential well, and they move with fixed binding energies and not in fixed orbits. That, as far as spectroscopy is concerned, there's no difference. But it does make some difference to how, well, we don't have to postulate anything to get these orbits, well, apart from the screening effect, which I think is obvious. There are other conservation rules. The other one is, why do electrons pair? Well, their angular momentum of half-hbar is the whole mass rotating at the speed of light in a radius hundreds of times larger than that of a proton. They're a powerful gyroscope, and just like any other gyroscope, they need to exchange angular momentum with something. And that is done, they just exchange photons, and their rotating photon structure means they're continually emitting and absorbing photons that generate electric charge. So electrons just pair so that they can move freely. So now electron pairing between different atoms, as we know, is the foundation of chemical bonding and molecular structure, and what enables us to build the universe, what enables us, or what is responsible for the world we see around us. But another thing, we come to bond angles or bonds. Now, we just consider, I think we all know that carbon has tetrahedral bonding. All their four bonds are as far away from each other as they can possibly get. And all that happens is that each, in the case of methane, you have one electron from a hydrogen atom and one from a carbon are bonded and forms a pair of electrons. These pairs get as far away from each other as possible, and that's what gives the tetrahedral structure. All of the bonds between all of the four angles on methane and on carbon generally are as far away from each other as possible. On the other hand, nitrogen has three electrons that can bond, and when they bond, nitrogen has, and when they bond one each with hydrogen, these angles are as far away from each other as possible, but you have two electrons on the top that are unbound. Well, they're bound to each other, but the charge that they generate just pushes these angles down a little bit. With oxygen, you have just two electrons will pair with two atoms, two electrons from, say, in hydrogen. The bonds will be as far away from each other as possible, so they're 180-degree opposite. You have four electrons on the top, and those four then push the bond angles down. I think these are pushed down by about 10 degrees. These are pushed down by about 30, 35 degrees, somewhere around there. But the angles of other molecules just depend upon local structure and residual electrons. I'll just leave that for chemists to study, but I'd just like to give you an indication of this is how it can happen. Look, I know other explanations are possible, but this is also equally valid in my opinion, because it comes fixed with all of the other things like special relativity, corrections, and so forth. Now, just as a brief conclusion, this has been a brief introduction to rotating photon particle physics. It's a discrete particle theory. It uses three space dimensions and time, known particles, physical principles, and constants. respectfully suggest it unifies electromagnetism with the fundamental structure of matter particles, with Einstein's special relativity corrections, the de Broglie wavelength, the origins of charge, elementary particles, the strong nuclear force and nuclear structure with atoms and the origins of their chemical properties. It's matched many observations and made many testable predictions. It's answered many questions that eluded nuclear physics for decades. What is nuclear binding? The reason for its short range, the structure of nuclei, the nuclei skin effect, and more. It's been a physical description. It's done without complex maths. Pythagoras' theorem, as I said, gives special relativity corrections as well as the de Broglie wavelength. Much of the rest of the maths is available elsewhere. I'll get onto that in a minute. I think we've all been known, people have been searching for been using field theories, and some suggest that particles are just manifestations in a field. I respectively suggest that particles generate the fields, but in the searching for quantum field theory, unified field theory, a grand unified theory of everything has been difficult, and progress has been slow, if it can be called progress. I'd just like to suggest that perhaps time to try a unified particle and field theory. If starting out with a field theory, as I mentioned before, a photon is an electromagnetic field. If you get it rotating twice per wavelength, you get the particle. So you can start with a field theory and generate the particles and in turn the fields. And I think that would personally think that's a better way of working. I'd just like to leave you with a little bit of something. There are those who have the sort of not invented here syndrome. I'd just like to mention this physical study has been extended to include the properties of nuclei that alter a property of free space. The radial differential of that property gives gravity. Newton's gravity, Newton's inverse square law is the first approximation. Einstein's field equations is the second approximation. The exact solution predicts the torus shape that has been imaged in galaxy centers. It and many other answers that you may have can be found in this book. Further details on aspects of what I presented, go to the Quasical website. Now, I suggest that I've outlined there the properties of all known stable particles, how they combine to shape matter, and given the briefest introduction to gravity. I'm going to leave you with, just to indicate, this gives all a table of contents of the book. It gives you all of the topics that I've discovered, all the topics that I have written on. It's been very extensive. Not much has been published because I found out a long time ago, reviewers don't like non-standard model presentations. This is not standard model. I just decided to finish the study before taking too much, but I will acknowledge, yes, the UK Institute of Physics was good enough to publish that paper on the physics of Einstein's gravity. Thank you for your attention. My apologies for that little mess up somewhere we got started, but over to you. Any questions?
Thank you.
Thank you.
Thank you very much for a great talk. And yes, you cover everything. And yes, I have also attacked many of these questions with a bit different maybe answers. So maybe let's go to the discussion. So everybody is welcome to unmute and comment, ask.
May I ask something? You mentioned that photons rotate twice per wavelength in the beginning. Why do you have this idea?
Well, it's that is the foundation of the model. I mentioned, I used only known physical principles, although the physical principle of E equals mc squared was known since 1905. The physical principle of the interchange between particles and photons has been known for about 60 years. It just so the way I worked it out was to start out with that model and solve from I omega was half h-bar to E equals mc squared. I could have gone the other way around, started with E equals mc squared, which was physically known, and worked back the other way and get I omega equals half h-bar. But the two revolutions is because they're the only combination where the magnetic fields overlap and the electric fields are on the same side, on the same quadrant. And no other combination does that.
What is then the structure of the photon if it rotates the point, or what do you imagine for a photon?
Sorry, my hearing's not all that good, I'm afraid. Can you go a little?
What is the structure of a photon? It's a point, or it's a massive point, or what is your picture from it?
The mass of the photon is just it's h nu, Planck's constant times its frequency.
So it's an integral over energy density, or what is it? Is it a field?
It depends on the units of that you use, but it's defined as electron volt. Well, it can be defined as any mass unit. It's usually in this situation defined as MEC per c squared, but it can be its mass can be defined in kilograms, in joule, in grams, whatever dimension you want. It is its dimension. H nu is a mass dimension.
Viv, would you mind to stop screen sharing?
Sorry?
I think if you stop your screen share, it'll be easier to converse.
Yeah. How do I turn off my stop share? No, I did the wrong one.
That's correct.
Supposed to do that one. Okay. Yeah, sorry about that. So questions again?
Okay, so one issue I have is that there are some nuclei with additional neutrons. There are halo nuclei, like helium 6, helium 11, helium 8, lithium 11, and they have 2 neutrons usually for a very long time, like a few milliseconds. Could you have this binding of for a very long time of neutrons in distance, a few femtometer distance?
Yeah, the neutrons, of course, you can get magnetic binding when the neutrons have the same spin and are close to each other. They can get magnetic binding. There will be some repulsion, but if they're not quite in the same plane, that you'll still get the magnetic binding, but you won't get as much charge repulsion.
So I don't think the magnetic binding is sufficient. You have two neutrons for milliseconds in distance of like 5 femtometers from the nucleus. You have 2 neutrons, and they are binded for milliseconds. So it is much farther than nuclear force class standard view.
What sort of distances when you say they combine for 5 seconds? What sort of distances are you talking about?
Like 5 femtometers from nucleus. There are two neutrons binded for a few milliseconds.
Oh, I mentioned, or I showed earlier, that 2 electrons could be magnetically bound to each other. There's no reason why 2 neutrons on the same spin can't be magnetically bound to each other as well.
Electron, I think you are talking about Cooper pairs. this is in a lattice and there are very large distances. But here I think it's a bit different mechanism. But maybe similar.
Yeah. Like the same thing, you can get, as I showed with that electron entanglement, there is no reason why that can't occur also with protons, neutrons. It has to be set up correctly and it could last for a little while, but I don't know the exact conditions, but this model doesn't exclude it as far as I'm concerned.
Okay, so for Coulomb interaction, I think what you have shown is that there you need some direction. So it should depend. Does it depend on the spherical angle from the Coulomb interaction in your picture?
No, the Coulombic interaction I was talking about is where they're in the same plane and the charges overlap. And that very short overlap. I mean, if you take the standard model where charge is distributed throughout the whole molecule, the chances of binding, electromagnetic binding, or electric binding are just non-existent. But when they are generated in the same plane and overlap, then you've got this division by zero situation. And very small charges overlapping directly can give rise to quite strong forces.
Okay, so for two electrons, indeed, there are these problems with very low distances, and so they are observed, for example, in the running coupling effect, that you have deformation of Coulomb interaction for very low distances, and it should be recreated in the model. But for long distances, do you have this? I think I have seen an image with some two planes for electrons. So which suggested that you have dependence on the spherical angle, while in nature you don't have such dependence.
No, I didn't quite understand, but this curving electrons won't occur. All motions will be basically straight line until photons are exchanged. I'm not really sure what you're saying.
I think he meant that charge is, spherical is symmetrical, right?
Yes,
and it looked like in your
Coulomb
model
is
it was
spherical.
not exactly. Is that what you meant, Jarek?
I thought I have seen some slides, some like at the beginning that which suggested that Coulomb interaction in your model is not spherically symmetric. But
you can't get nuclear binding. Certainly, the standard model treats charge as symmetric in 3 dimensions. I'm suggesting charge is symmetric, but only in 2 dimensions. Yeah. And the experimental measurement of the charge distribution for protons and neutrons gives a very, very strong indication that is the case. Because particularly the central point of that curve is 0. And the only way you get a 0 central with something charged is if the charge is either cylindrical or planar. You won't get a 0 center if charge is distributed uniformly.
May I ask another question? Is your model a particle model or a field model? And what is your Hamiltonian?
I describe it as a particle model. I describe it as a particle model. The particle is the photon, but the photon is a field. A photon has electric and magnetic fields, and that's all a photon is. It's just electric and magnetic fields. So we start out with a field, which is the proton, we get it, the photon, when it rotates twice, it generates the particle. From then on, that particle generates all the fields. And as I suggested there, they've even got gravity thrown in as well. They're generated by the particles. But the particles themselves are generated by fields. The fields being the photons. So
do you have a Hamiltonian? Do you have a Hamiltonian, an energy expression?
Lagrangian.
sorry, so what was that,
Do you
David?
have an energy expression and some function for energy? Like in quantum mechanics, you have Hamiltonian and wave function. Do you do some calculations on this model?
I've done a lot of calculations. They're in that book to which I made reference to, and I will be posting more. I've got some of it is already posted up on the Quisicle website, and I will be posting more there later. Most of the calculations are done, but as I pointed out at the beginning with Einstein's relativity theory and the way the mathematicians have used it, they've just made, I agree that his mathematics was complex, but there's no excuse for not reading it and understanding it correctly. And I just would like to suggest that if you use mathematics only without a physical support, without a physical reason, you are likely to run into that situation. And I know the cosmologists, the theoreticians will say black holes have been proven, everything else is proven, but Einstein didn't believe in them. The only way Mercury's orbit can precess is if gravity is weaker than inverse square. And if the sun's gravity is weaker than inverse square, then the gravity of every other star is also weaker than inverse square. So the gravity in space is actually weaker than inverse square. And that has significant consequences for cosmology. And what I'm trying to say is that if you just use, like the theoreticians who believe they understood Einstein's field equations and expanded on them, and he points out many times that his work was approximation, that no matter how good or accurate your work is, if you're starting out with approximations, you're going to finish up with approximations, and to try and get some magic meaning out of approximations is not the right way to go. And that's why I suggest, look, go the physics first principle. And Einstein actually, in his 1911 paper, calculated the physics that he used. I think he went to field equations because Einstein, not long before him, had published some work on trying to relate electromagnetic fields to gravity. And I think he was just repeating, or believed he could repeat that same sort of mathematics. But please, I've used the physics first and then the simple math. The math, in my situation, I think the maths is much simpler than what other people are using. I've justified everything. I believe I've justified everything that I've used. And I'm not, I think people should be very careful about using mathematics. You've only got to get one little thing wrong. And in the case of Einstein's work, yes, he did mention terms with the minus sign more often than he did the terms with a plus sign, but he also stated at the beginning with that minus sign that they were approximations. And to suggest that exact solutions to approximations are exact solutions is, they're only ever approximations. And that's why I'm in favor of describing the physics first and then using the mathematics necessary to support it. And that's what I believe I've done in this case. And I think, well, I hope some of you found it useful. And for any nuclear physicists out there, I think you'll go much better using this model than trying to continue the way theoreticians are going at the moment.
I
Did
thought it
you
was
have-
really interesting, and I also see some similarities between your model and the model from Robert Close. Unfortunately, he had to leave, but I was wondering, have you read his work as well? Or maybe I can send you a link.
I've read some
I
of
saw some similarities.
I've read some of his work, not
Mhm.
all of it, I'm afraid.
And so I was wondering, do you have any thoughts on what that field is, space? Is this, in Robert Close model, it's an elastic solid. Do you have any thoughts on that? What that field is that everything is based on?
Space is empty space. It's got nothing in it. Well, that's not quite true. The one thing that space has everywhere is cosmological neutrinos. So you can never have this pure thing called empty space. The actual density of those, under this model, the density of those cosmological neutrinos is something like, I don't know, 10, in approximate and broad figures, 10 to the 10th per cubic meter, or that sort of thing. So there's huge numbers of them. They are everywhere. In fact, I have shown that they do have an effect on space, but that effect is spread over hundreds of thousands, or more likely hundreds of millions of light years, or tens of millions of light years. That effect is spread over. Its local effect is almost not detectable. It's not detectable. But space is, I've seen some people have come up with ideas that space is very dense and all sorts of things can happen. But that's a mathematical solution. Space is space. The only way space can expand is if the electric permittivity and magnetic permeability vary. That's the only property it has for space to expand. And I've got no indication one way or the other whether that is occurring, but I think it isn't. I can explain everything, including photon redshift from distant galaxies, without the need for an expanding universe, and without the need, and under terms that satisfies the Tolman test. That's not a great deal of difficulty.
We should have a mini conference on that topic as well. I think that's very interesting.
Sorry.
Yeah. I think we should also have a mini conference on that topic as well some other time. That would be great. Yeah.
Well, I will be giving some further talks to Quisicle at some time in the future. If I don't have any great difficulty, I could, maybe we could combine Quisicle and particle physics. Yes, but in the end, when you understand the physical origins of gravity, you will answer a large number of questions. And when I talk about the physical origin, I mean, you may have seen there on my third slide, or whichever one it was, the different fields. Newtonian, 1 over r squared, Einstein, 1 over 1 plus alpha over r times r squared, and 1 over r squared e to the alpha over r. The dominant part of the theory is Newton's 1 over r squared. And it applies in most cases. I think Einstein was probably a little brash to suggest that Newton's theory was a first approximation to his. Okay, yes, it is, but Einstein's mass distorting space-time, he didn't explain what space-time was, nor did any of the people who read it, but it should be rather obvious that space-time distortion is redshift. When redshift occurs, distances become longer, times change. That's space-time distortion is redshift, but he didn't mention that. And I've got no idea why, because he used it. Redshift is alpha over 2r.
Hey, Vivian, this is Chandra.
Yes, Chandra.
Basically concur with your assessment about the space property, dielectric constant, and the magnetic permeability. They are of profound importance, and they are physical properties of the space as Maxwell's equation has validated by 1876, I think. And we are neglecting them and folding them into C or C square, calling that as a fundamental constant. C is never a fundamental constant. It's a secondary parameter derived from epsilon naught, mu naught, or in a material medium, epsilon naught, epsilon and mu. Because C is a derived parameter.
Well, to me, the concept, the fundamental concepts, the only ones I use are charge E, speed of light C, which means epsilon naught and mu naught.
They are more fundamental to me.
H-bar or H, I forget what the other one was. They are measured. I mean, many people have many different theories. I think the objective is of a theory is not to produce beautiful mathematics like the standard model does. The objective of a theory should be to match experimental observation and, if possible, make predictions that can be tested. Now, just that what I've done, I've matched a lot of experimental observations. I've explained some, like the skin effect, that had no previous explanation. And I have made in all of this work predictions that can be tested. Now, if a theory has been forwarded and other things are fundamental or something like that, it's the use of that is in its ability to match observation. And I regard that as the test, not how good somebody's mathematics has been.
Yeah, those are positive things. Thanks.
Do you maybe have some intuition why there is different sign between for Coulomb repulsion of the same signs, while for Newton we have attraction? Do you have some intuition? Because this is very difficult. We are trying to understand it with Manfred.
I realized that I went through my presentation very quickly as just a broad introduction that I wanted to give to show that the particular model was useful in explaining a number of things that have not previously been explained or giving different interpretations. In all of this work, I don't think if you think I'm wrong, I've made no assumptions. The assumption that the rotating, I've made no assumptions that were not proven. The rest of it, my concept is that it's up to nature. Nature does what nature does. It's not up to us to tell nature, look, you should bind, electrons should bind in pairs because of somebody's law, or that they are, that orbits, that the electrons have to travel the way they do because their orbits are quantized. It's up to us to find out how nature obeys by studying it, not by telling it what to do. So I don't believe I've told nature what to do in any of this, other than in my.
No, I disagree here. So we should find some very simple rules which allows to conclude what nature does. I think this is the main goal. So there are this standard model is a set of such as rules, but it is quite complicated, like 20 parameters. So could we get simpler rules so that they agree with what nature does? That's the big question.
Well, I'm going to stick with, I'm afraid, Jarek, my hearing isn't as good as it used to be when I was young and good looking like you. If you need to could talk a little bit slower, or I'd be quite happy to answer questions by email, but I'm going to stick with my earlier comment that the object of a theory is to predict or to match observation. And and it's no good, I would say this, it's no good just having a theory that, okay, you've got a Higgs boson, for example, which you can use to predict the Higgs field. But if you don't know what's causing gravity in the first place, the physical origins of gravity, postulating that it's a Higgs that's generated by a Higgs boson really doesn't give you any good. If, on the other hand, you could use the Higgs bosons to turn around and derive all of the properties of gravity, including, for example, what they consider as black holes, well, go for it. But if you're not there, it's not that useful a theory, in my opinion. Yes,
Viv, if I'm not mistaken, I think Jarek was asking why electromagnetism is both attractive and repulsive, whereas gravity is only attractive. Is that correct?
Yes,
why the sign changes? It's a very difficult question.
Yeah, that's because of the differential of properties of space and differential. All photons have mass. Has anybody read Einstein's 1911 paper on when he calculated the redshift from the sun? And he did that just by calculating the effect of Newtonian gravity on photons with mass. If you read that, you'll find that he attempts to describe the bending of the light rays around the sun as being due to a change in the refractive index. Yes, well, his guess was quite good. There is a change in the refractive index of space, and it doesn't matter whether the mass is, whether it's a particle or an antiparticle or a photon, the response will always be the same. So there's no such, well, according to this, there is no such thing as anti-gravity. And besides, anti-gravity is not going to do you any good traveling through space because there's no gravity to travel against. Sorry about that. Might be good for I suppose the best anti-gravity they've got so far is these things called rockets. They're pretty good.
Yeah, and Jarek is asking why then is in electromagnetism repulsion and attraction.
So maybe.
Sorry, I understand Arnie real good. Would you mind acting as an interpreter? My hearing, I'm not as young as I look. Would you mind, could you?
Manfred, were you asking why electromagnetism is both attractive and repulsive?
Oh yeah, well, it's opposite charges. Yeah,
this is simple, but why Newton is difficult.
Well, I suppose I could turn around and say, well, if you can always try the experiment. You can just do it as it is. I would have accepted that as a normal that's established in nature. I guess, I think with electricity, I would respectfully suggest that it has been answered by QED theory. So that takes care of electricity. My understanding, and I've tried to have a look at it with magnetism, I haven't spent too much time on it. But I gather by you asking that question, nobody else has written the answer either, other than that when you get two magnets together and you point the poles together, the opposing poles, they attract. That's all I can say. So yes. I'd say when it comes to charge, QED handles it. When it comes to
I guess the problem I see there's no real physical explanation. At least that's what drives me. I want to understand why these magnets push each other away, because exactly how, right? So we are all trying to find a model that would explain this from like first principles or something. You know, like Robert Close model, that's the one I understand the best. Like in his model, right? For instance, space is an elastic solid and everything is waves, just like in your model where you have, you know, an electron is composed of actually photons going twice around in his model as well, and it's all based on elastic waves in elastic solids. So this model, for instance, can explain gravity, but there I don't see exactly what charges. I don't understand it yet. So, you know, it must be some effect based on wave interference or something, but like I just want to know why. Like why? Why is there plus and minus charge exactly? Like physically, you know, that at least that's what I would like to find out. So
just very briefly on that, physically the difference between positive and negative charge is because there are positive and negative electric fields. And the fields are caused, they're part of the photons, they're conserved. You have a positive in one direction means a negative in the other direction for conservation purposes. So the fields, do you accept that, first of all, that positive and negative electric fields can exist and do exist?
oh, totally. But just like I don't see like why. I want to know why. I don't think anyone can answer that yet. That's why we're all here. Like fundamentally, why, you know? Anyway, that's probably, I don't think anyone can answer that. It's just, at least in my head, I always ask that question.
Do you know the Sine-Gordon model?
Yeah, of course, exactly. Yeah. We talked about this. So that's exactly, this would be an explanation. And that's why I like your model.
You have
at least that part.
Screws.
Exactly. Yes, Sine-Gordon. Totally agree. That would be an explanation.
And left
yes.
screws and right and
yes,
right.
Totally. Exactly.
And right
yes.
and left attract each other.
Totally. That would be an explanation. That's what I mean. Yes, that's an explanation.
Yeah.
But it doesn't explain everything yet, right? It explains some parts and then it doesn't explain some of the things.
I can offer a little bit of a statement about mass. You know, why do things have mass? And it's, if we summed up, that the photons don't travel through space infinitely fast. Space offers some resistance to them through epsilon naught and mu naught. The resistor, a property of mass is its ability to resist inertia. Well, space is doing the reverse. Space is resisting inertia, and in doing so is imparting mass to the particles that are moving through it. So that will take care of mass. And you'll find...
I didn't, was too fast. Could you repeat?
There are many masses. There are 4 masses at least, types of mass.
Well, yeah, I also think the comments, there's a difference between rest mass, right? And the mass you derive from the energy. And I think there's some conflict of we use the same word, but you mean different things, really, right?
As 4 masses, I mean, there is mass as energy releasing annihilation. There is mass as inertial energy. So these 2 are equivalent from special relativity. But we have also the other 2, mass in gravity, which is, we don't know. We know for bulk matter, but for electrons, we don't know. Experimentally, there was 1967, this Fairbairn-Wittenbaum, we don't know for electrons. For antimatter, there are hypotheses in both sides. If they are attract or repelled, we don't know. For gravitational mass. And there is 4th, there is this, the Broglie mass for the clock, for the zitterbewegung clock. We know for electron there are experimental confirmation. For the others we don't know. There is just hypothesis. That's all.
I respect.
Viv, could I suggest that you take us through your explanation of the radial differential of epsilon mu as a result of the nucleon rotations generating the gravitational effect?
Yeah, okay. Well, first of all, just before I do that, I know that several different masses have been proposed, but I've never seen anything to suggest that those masses are other than the same. And under this model, they will all be the gravitational mass, rest mass, inertial mass. I haven't seen anything that suggests you add energy to an accelerated particle. To accelerate it, you add energy, and that energy is absorbed by, it's just taken up as increased mass due to the relativistic corrections. Anyway, what Arnie is saying, okay, I'll tell you this, the actual origins of gravity. Protons and neutrons have very high frequency, and as Feynman pointed out, high frequency changes the electric permittivity of space. Now, if you have enough nucleons with a very high frequency, it doesn't take terribly many nucleons before you reach the Planck frequency, which is the inverse of Planck's time, which is the highest frequency possible. So when you have a huge number of oscillating electric fields associated with nucleons, their number builds up, and the number required to get to Planck's frequency is way under 1 gram. Then all that's happening is that the photons in a mass are just distorting the electromagnetic field around them by changing the electric permittivity by their huge amount of Planck's frequency generated by the nucleons being out of, they're not synced. Planck's frequency is about 10 to the 44 hertz. Nucleons are about 10 to the 23 hertz. So by the time you have about 10 to the 21 nucleons, which is I think under 1 gram or something like that, you're reaching the Planck frequency. And now it just takes a huge number of these Planck frequency oscillations to start distorting the electric permittivity of space. The differential of the electric permittivity of space gives the inverse square, Newton's inverse square law as the first approximation, the Einstein's approximation as the second approximation, and the exact solution predicts the existence of those structures seen at the center of galaxies. So when Einstein in 1911 wrote his refractive index depends upon electric permittivity, when he was talking about electric permittivity, well, that's basically the origins of gravity. Linear photons respond just the same as rotating photons because they're frequent. In all cases, the frequency, the Planck's frequency at about 10 to the 44 hertz is so much lower, so much higher than the other frequencies, photons or whatever they are, and nucleons are about 10 to the 23. They're just, the difference is so much that they all respond the same. And it doesn't matter whether you've got a proton or a positron or an electron or whatever, they're all photons, they'll all respond the same to gravity. And of course, as you can see from that, that leaves absolutely no space. It matches everything that Einstein's done. It matches everything that Newton's done. It matches everything that's been observed. That's gravity.
So are you saying it's essentially a refraction towards the increase in electric permittivity?
Yeah, the speed of light is determined by the electric permittivity, but the diffraction is determined by, the bending of light is determined by the differential of the electric permittivity. And it's that differential that gives rise to gravity. And that's why it requires such a, it's still an electromagnetic effect, but that's why it requires such a huge force. That's a huge mass to get some distortion. And that also gives, because mass of mutual attraction, M1, M2, mutual attraction, well, the refractive index change introduced by one party will attract another and vice versa. It's got all of the properties of gravity, and it doesn't rely on anything else. And it's weaker than inverse square too. Which and it matches. I haven't come across anything yet that it doesn't match.
So do you think this goes all the way to basically infinity, or do you think there is, some limit?
It just peters out eventually. I mean, eventually you get to the stage, down here on Earth's surface, unless you've got some really, you can measure gravity, but you can't measure the differences between gravity at this height and this height unless you've got some super sensitive equipment, which I don't know about. But if we can certainly look at it, and you can look at this about this height, and I can let it go and it goes down. We know gravity works. But yes, it does extend to infinity. And just between you and me, gravity extending to infinity, when gravity is less than inverse square, is the reason why a steady state universe won't collapse. No, you do the calculations. You find out that when gravity is less weak in the inverse square, you just do the calculations. You find out that gravity tends to zero at infinity, and it gets to practical zero under quantum terms well before that. So that's why I suggested earlier that I think the cosmologists have been headed in the wrong direction for a long time. And the best example of this is every time they've got an improved telescope, they say, wow, we've now got these fully grown galaxies, huge
I know,
galaxies.
exactly, right? I totally read all this stuff as well. Yeah.
Huge galaxies
Mm.
that were first explained as being 2 billion years after the Big Bang. And then along comes Hubble, and they explained 1 billion or 100 million or something. Now what are they talking about? I don't know. It happened instantly with the Big Bang. Forget it. They are just wrong. And well, I've been in, as mentioned earlier, I've been in business for a long time. One of the things I found out in business is that if you're wrong, if there's something wrong in your organization, you better be the first to know. Unfortunately, when it comes to cosmologists who think that they are world's best gift ever granted in terms of their intellectual capability, they don't want to be the first to know. Neither do they want to be the last to know. They don't want to know. You try telling somebody like Graham Greene that he's doing a world tour at the moment. You try telling him there was no Big Bang. They don't want to know. They've got this wonderful mathematics that they think nobody can understand. And my apologies to any mathematicians, but anyone who is any good at mathematics and physics would have at some time looked at Einstein's Foundations paper to see if they could understand it. Well, nobody did. Well, present concluded. And they don't want to know. And all I'm suggesting, yes, okay, there are some things I didn't handle. I mean, the origins of positive and negative charge attraction. Yes, that's handled by QED theory. No, I'm really not interested in finding out what causes magnetism. I'm quite happy with the effect that you get two magnets in the right poles. I've worked on it a bit. If somebody was interested in cooperating, yeah, maybe we can do something, but I have no great interest. It works.
So regarding magnetism, if you have Coulomb interaction and Lorentz invariance, then like in Feynman famous lectures, you get magnetism automatically from Coulomb plus Lorentz invariance.
Well, okay, if you've got an explanation, that's fine. I had no.
So you need the Coulomb, but I haven't seen that the Coulomb in your derivation.
Well, yeah. No, it's one of the things I have no interest in working out. I think having gone all of the way, starting from nucleons and building everything up and building up to gravity, and it's all under the one banner, all under the one model. QED has done a good job with charge. I'm quite prepared to accept that, even though I don't possess to be able to make QED calculations.
So
But
Coulomb is obtained experimentally, for example, in liquid crystal experiments. So it's not a problem to get quantized topological charge, and you look at acceleration, and it agrees with Coulomb interaction, for example, and they get this kind of experiments. So it's not that difficult.
Did you understand that, Chantal?
Well, I think you're talking about your model, Jarek, right? Well, so of course, everyone here has their model,
I'm
right?
talking about experiments.
Jarek is talking about magnetism.
Experiments. I'm talking about experiments on liquid crystals. They get Coulomb interaction for quantized topological charges. I put some articles in the chat. So one, you have Coulomb interaction. Second, Coulomb interaction. So it's not that difficult to get Coulomb interaction and charge quantization. You have topological charges, and they effectively, for example, you look at and it agrees with Coulomb acceleration. So they experimentally get Coulomb interaction in liquid crystals for topological defects. So I'm not talking about any specific model, but just about experiment.
Any other thing I would add about, I would like to suggest about, there are many other models available, and this is one, but unless you model, I would suggest that some of the answers I gave for nuclear physics are just totally, I mean, nobody knows what the skin effect is, or they don't know it. It's been puzzling them for a long time. I suggest that gave the answer the same as it gave. Nobody knows the physical origins of Einstein's relativity. I suggest that gave that answer, and that the model yeah, sure, I haven't answered why magnetism is attractive and repulsive, but it just is. I haven't answered why the charge of the magnetic moment of a particle is charge times radius. It just is. But the rest of it, I think I've done a reasonably good job of going all the way through, and do respectfully suggest I know
I
particle
completely
physics.
agree, but there are these holes at the bottom, so it might be worth to try to fill them. Yes.
I've also been trying to think a lot about this. I mean, if we agree that everything is based on photons, whether they're rotating photons or linear photons, so that's electric and magnetic field 90 degrees to each other, which I think I would argue they're not really separate. They're just two manifestations from different points of view of the same underlying thing. You can't separate electromagnetism. So it's really a topological effect, in my opinion. When you create an electron, you're creating a flow that's going in one topology, and its magnetic field will therefore orient in a different, you have axial versus equatorial. So as soon as you have a rotating system, you're going to have chirality, which is going to be north from one perspective and south from the other. You can't have do we have magnetism in the absence of electrons? So, it's like chicken and egg situation, but they're intimately related to one another. They're just opposite sides of the same coin. So I don't know if that makes sense.
I would suggest for experimentalists that perhaps you could try to bend a photon around its electric field, and then you can get a magnetic monopole.
Yeah,
Sorry
couldn't we
about
do this like experimentally, right? Exactly. Yeah, that would be cool.
You could get it.
Well, John talks about that. John talks about
bending of photons.
Yeah. John talks about that it would decay instantly into an electric monopole because a magnetic monopole would require too much mass.
Yeah.
So it cannot.
My own impression it would be, I won't say impossible, but next to be exceeding impossible to get them to bend around their electric field and the magnetic field. But that's nothing to stop people trying. But that's the only, if you're looking for a magnetic monopole, I think that's the only chance you've got of getting one. Okay.
Any more questions? It's really late for you, so for you it's like probably 3 o'clock in the morning. So
You're happy, Chantal, are you happy with that explanation for quarks?
Oh, I thought that was great. No, I really like that part. I think that's really awesome.
Okay.
Can I put it on YouTube? Is it okay if you put it on YouTube?
Sorry?
Is it okay to put the video on YouTube?
That particular part of it, there's a couple of episodes on YouTube. Go to quasical.com and search for me, and you'll find nuclear binding and nuclear structures, which go into, both of which go into what I've introduced you to in much greater detail.
And can we put this video also on YouTube? Is it okay?
Well, yeah. As far as I know,
Okay.
It's going on YouTube. I just hope you leave that bit out where I pressed the wrong button because I didn't know what I was doing.
Oh, it's okay. It's no problem.
And the last question, if I may ask, spin for you is the same as a classical, orbital momentum. Spin doesn't have, you don't treat it differently than any other angular momentum.
Can you interpret, please, Arnie? I'm afraid my hearing
Oh,
is not.
if I heard correctly, he's asking if you treat spin differently than the traditional angular momentum from quantum mechanics. Is that correct?
Yes, spin in all cases, what quantum mechanics guys call spin is just angular momentum I omega, which mr squared, and times c over r. And as I said, that's why the very, very small mass of a neutrino is why a neutrino can still carry away the same spin as a proton, which is what, 10 to the 20 times more massive, or 10 to the minus 10 times, 10 to the 15th or 14th times per massive. It can have the same spin because it's 10 to the 14th times less diameter. But spin at all stages, spin is angular momentum, as was originally forwarded by Coulomb, by the Germans when they did it. I would point out.
Uhlenbeck and Gauss-Smith.
Uhlenbeck and Gauss-Smith, yes, thank you for that. Sorry about that. I would point out, I was going to raise.
So not only angular momentum, but also magnetic dipole moment of spin. It is also crucial for spin.
Yeah,
magnetic dipole moment also.
Yeah, I think what I was going to say is that very early on, after electrons were discovered, their wave properties were known. Now, when you have people like Dirac and Schrödinger, they know nothing about an electron. They really had no option but to try and treat it as a wave. And they did a good job and extended it okay. But the problem is quantum mechanics has gone from the limit of the smallest size particle that you can have, which is quantized, to saying that everything which is quantized is a wave. And then they're treating everything as a wave. And that's sort of wave. The waves have fields. Field theory originated. The mathematics is very, very complex. But they persisted with it in the absence of anything else. I respectfully suggest that something like this model has shown has been rather useful, particularly in nuclear physics, but in other areas as well. And that people would, using this model, as I said, the model is one where a field generates the particle and then the particles generate the fields. But so to some extent, could be considered a unified field theory, because I said we start out with particles, start out with fields, generate particles, then use those particles to explain all the other fields, including gravity. But I think it's better that just you have particles, treat them as particles, and I think they'll get further. Really, I think the standard model just leaves so much to be desired. It explains so little, and every time they get a bigger toy to play with, except for the, or even the James Webb Telescope is now presenting with problems that they can't say. How do you get a fully grown galaxy the size of Andromeda, or our galaxy, couple 100 million years after the Big Bang? Well, I'm sure some mathematician will come up with some way. But isn't it just simpler? Look, the gravity is weaker than the inverse square. That's proven by when Mercury orbits the sun. So gravity is weaker than inverse square for all suns. Therefore, it's inverse square. An infinite universe is stable. I mean, when Einstein found the redshift and attributed it to, and it was attributed to an expanding galaxy. Now, if you read Einstein's paper, he only considered a finite universe. Just between you and me, it doesn't matter what form of gravity you have. A finite universe, even if gravity is weaker than the square, a finite universe will still collapse. It is only an infinite universe that won't collapse. And the infinite universe, you can build a telescope 10 times more powerful than the James Webb telescope, if you want to. If it is physically possible, all they're going to do is seeing the same thing in greater detail.
I agree, because, you know, one rotation of the Milky Way is about 200 million years. So if you want to have a mathematical model of building a galaxy, it takes many rotations, right, to build a galaxy. So it takes billions, or at least more than a billion years. And that's the problem. Yeah, I see as well. Yeah.
Yeah, and the worst thing, and I'd love to get somebody who believed in the Big Bang and say, okay, well, guess what your maths indicated? You got a 1 in 10 to the 60 chances. So how do we double or nothing, $10 at a time, and winner, you can either quit, or if you get to 10 to the 60 and you correctly picked it every time, you'll be a very rich man. But frankly, I think you'll be broke by $50. You'll lose $50. You won't even get that far before you get it wrong. Maybe $100 or something like that. But those odds are zero. And mathematicians don't seem to realize that. They don't want to look for something else. You know, the observed redshift, which they said is predicted, is an indication of the expanding universe, is exactly what you'd expect in an infinite static universe. Exactly.
So how does light lose energy in your model? Like, do you have a model for how light loses energy over the distance?
Well, it's the same way that particles lose energy. I mean, you know, almost all the cosmic rays we have in our galaxy come from within the galaxy. To put it, the easiest way of wording it is, if you ever had a look at, you've seen pictures, or you've obviously seen pictures of galaxies and the spiral arms are going around. Yes, you've all seen spiral arms on galaxies, and the spiral arms lag the rotation of the galaxy. If it was only on 1 or 2, we could explain something, but they all do that for the simple reason that there is a universal drag factor throughout the whole universe, otherwise known as cosmological neutrinos. They exist in huge numbers. They have the property that they slow down things. They create what you'd call a viscosity. They have a property that they slow down things according to their momentum. And as a for instance, we all know that Mercury should orbit the sun, losing 43, or with a 43 arc seconds difference between Newton's prediction and Einstein's general relativity. And I get the same prediction in my calculations in that paper I referred to at the beginning. But Mercury's actual orbit has been measured at about 41.8 arc seconds per century. Something is slowing it down. And the only thing that can do that, which it actually does, is there is a universal drag that slows the photons down according to their momentum, and it slows every particle down according to the momentum of the individual particle. So it slows cosmic rays down and traveling in interstellar space, and very few make it more than 2 or 3 galaxies distance, and that's been known for a long time, but it's attributed to slowing down by the cosmic background radiation, but that's very, very slight compared to the number of cosmological neutrinos. And that same calculation shows that for a single nucleon orbiting at Mercury's distance, it will be slowed down by about what the difference between what Einstein and I predict and what is observed. So there is this universal thing that is slowing everything down, including photons, and that's all the redshift is. And that's what, and Hubble at the end of it, towards the end of his career, believed it was something like that. That particular effect, it also satisfies the Tolman test, or in Tolman's mathematics, he was a bit ambitious, I think, and he tried to find every possible excuse that he could get. But it wasn't very good, and this effect gives the same Tolman test answer as does the expanding universe theory. So, what more can I say? Anyway, if you're really interested, have a look at that. Go the website.
I'll take a look. I'll take a look.
Take a look at
Okay.
it. Everything is in the book. It took me a long time to do. That's why I've got a few grey hairs. But I did try initially to publish it, same early in my career. I tried to publish stuff that wasn't standard model, and I just got ridiculed from one end of the globe to the other. And learned from that, don't bother arguing with referees, a lot of whom they don't know anything than their own speciality, and they're not going to let anything get published that differs from what they think. And I just said, just get on with it. And I did that in my career, and then I finished up taking a commercial product out in the field, much to the annoyance of all the academics who said I was wrong and would never work. I made quite a successful living. In fact, successful enough to finance all of this own study myself. And I just learned out of that. Don't bother arguing with referees. They're going to find some excuse. I'll admit that I thought I was fortunate. The Institute of Physics, one of their journals did accept it. And yeah, I have nothing against them. That's the way it goes. I mean, one American publication, I won't mention, I wrote to it, and it was a similar paper to what the Institute of Physics said, and they came back with, the editor came back, oh, the mathematics isn't complex enough for our journal. I think that sums up physics at the moment. Fundamental physics has just been totally hijacked by mathematicians. They think that nobody else can understand them, which would be fine if they could understand maths themselves. But they've all, I mean, ALL, capitals, because nobody who's a physicist would not, who wanted to be a good mathematical physicist, nobody would not look at Einstein's field equations in his paper, try and work that out. They've all done it, they've all goofed it. And if those who disagree are quite welcome to write a letter of refute to the Institute of Physics, and I'll publish it, and I'll take great delight in pointing out why they're wrong. I'll be polite, of course. As I said, I've gone all the way through, started at the smallest subatomic particles with this model and gone all the way through to what the hell is gravity. If those who have, you're entitled to have another theory, and you can regard my theory as an opinion, but if you do have another theory, at least make sure it does cover more than just one or two things, and like structure of a it's so long since I've looked at some of the bosons, like the Higgs, the W or Z bosons, which last for about 10 to the minus 20 seconds or something like that. And somehow out of that, they've got to generate things in real life that have lasted for billions of years. Like, get real, it's just not going to happen. Anyway, I think that's about it, unless somebody has some more questions.
Yeah, I think it's getting really late, so thank you very much. Unless anyone has any questions.
Okay,
well, thanks for attending my talk, folks. And thanks for the invitation.
Thank you very much for great talk. Thank you.
Thank you.
Cheers.
Bye.
Bye.
Thank you very much.
Bye. Thanks.